Okay, so hi everybody. So in the last video, I talked about the law of reflection kind of from a concept point of view, just saying that it's a very fundamental aspect of how light interacts with surfaces, at least smooth ones. Now to try and show you some places where you can actually use this rule of thumb to calculate something useful, I want to do a few examples. Now, the specific examples I'm going to show are motivated by a particular type of optical element known as a retroreflector. A retroreflector is something that if light comes into it, the light bounces around, it comes back out the same, basically it leaves in the same direction or the opposite direction, depending on how you look at it, as it came in. So if you're sitting there with a flashlight by your eye and you shine it at a retroreflector, no matter how you hit it, you will see light come back. Again, this is all things like this are often used in road signs, etc., because then the headlights, no matter how they hit the sign, they send light back to you. And there's versions of these which exist on the moon, which are used in experiments where we basically take a laser beam, shoot it at these things, and since it comes bouncing straight back, you can use that to do things like measure the distance to the moon very accurately. Now, there's various ways to do this. Some of them involve little pieces of plastic, but the ones we're going to focus on here are actually just a few mirrors glued together. And we want to just understand how this works. And this is a good place to explore the law of reflection. So let's kind of build up to this case of multiple mirrors. Let's first consider a single mirror. And let's understand why this isn't a very good retroreflector. So we have a mirror here. It's just a vertical, simple sheet of metal. And there are conditions where this does reflect things back where it comes from. Imagine you had a beam of light that comes into it face on, straight on at 90 degrees from the surface. In this case, where does the reflected beam go? And don't worry about calculating it, just think about what you'd think intuitively. I think if you think about this intuitively, since it's completely flat and it's coming in straight on, it should make sense that in this situation, the reflected light, shown in orange, comes straight back out. So this is retroreflected. It's basically been turned around 180 degrees. Great. So in this particular geometry, the mirror does act like a retroreflector. But it only works like that in this one geometry. If we do something different, like say this, what if we have the light come in and hit the mirror at an angle? Is the light going to come straight back? Again, don't worry about thinking about calculating it, just think about what you'd think intuitively would happen given what we talked about in the previous presentations and just your own experience. No. In this case, the light would be bounced upward. Again, this is consistent with the law of reflection. Here is the angle of incidence is here, and there's an angle of reflection here, and they're equal to each other. But this means that the light gets bounced away from the direction it came from. So this light doesn't come back. So this doesn't work except under specific conditions. Now, this specific mirror shown here is actually part of a retroreflector. So it's worth understanding it a little bit. So let's try and do a more quantitative analysis of these situations. But we'll keep everything relative, keep the angles relatively consistent for a little bit. So let's consider a case where we have a beam of light coming in horizontally and it hits a mirror, which I'll now say is at an angle of 45 degrees. The question we want to answer in this problem is, where does the reflected light go? Well, if we want to answer that question in a quantitative sense, we need to use the law of reflection, that the angle of incidence and the angle of reflection are the same thing. Now, these sorts of problems can sometimes be challenging for people. It's not that the algebra is hard. The algebra is straightforward. This theta I and theta R are the same number. And most of the time you get a problem like this, that's all it's asking. The reason these problems can be sometimes challenging is because you need to be able to figure out what these are in terms of what you're given in the problem. If I told you the angle of incidence was 45 degrees and asked you for the angle of reflection, that'd be a fairly straightforward algebra problem, which you can solve using the same techniques we've used before. But since we're not given it in that way, and in many situations in real life, we wouldn't be given it in that way, we need to figure things out. We need to figure out what the angle of incidence is, and we need to figure out what the angle of reflection is measured relative to. And so I want to try and clear this up because this is often an issue that crops up when people try and do versions of this problem that don't explicitly say what the angle of incidence, angle of reflection. So since this is going to be a geometry problem, we're going to have to do a few sketches. And for this reason, I'm not going to try and draw it on the board just because that's going to go badly. But I'm going to go through a whole bunch of slides that kind of build up what the picture will look like. So when we're given a problem like this, we first have to make it quantitative. That is, we need to be clear how we specify directions. What are angles measured relative to? Now, for the purposes of using the law of reflection, the important direction is a surface normal to the mirror, something that makes a 90-degree angle to this surface. That is what angle of incidence equals angle of reflection means. So we need to be focused on something that can eventually give us this. When we say, where does the reflected light go? It becomes clearer to answer that if we say, what's the angle of reflection, which is the angle between this surface normal and the reflected ray. That is, if we're not asked for anything else, the number we're looking for. Okay. We know, so this thing, which is often designated as theta r, is the thing we're looking for. Fine. What do we know, going back to the standard approach? Well, we know the direction of the light and the angle of the mirror. Fine. But what we really need to relate these things to this angle is the angle of incidence. We need to figure out this angle here. And figuring out what that is, given information in a problem, is an exercise in geometry. And so that is sometimes hard to write out, but you can try and do it systematically. So again, we're hoping to use this rule, angle of incidence equals angle of reflection. But to use that rule, we have to figure out what the angle of incidence actually is. We have to figure out this angle here. Okay, how do we do that? Well, in this case, and in many cases, it's often easier to figure out this angle first. Now, the thing is, when I said this was tilted by 45 degrees, I meant literally the surface of the mirror is 45 degrees from the horizontal. This ray approaching the surface is also horizontal. So this angle here is also 45 degrees. Now, I want to emphasize, this angle is not the angle of incidence. Angle of incidence is this thing. It's now designated theta I, whereas this is theta R. We know these two are the same, but we need to get this. Since the ray is horizontal, this is 45. We know this angle is 45 degrees, just like this angle is 45 degrees. Okay, this angle is 45 degrees, but the angle between this surface normal and this is 90 degrees. So we also know this angle plus 45 is 90. Now we just have an algebra problem to solve, and it's a fairly straightforward one. 90 degrees minus 45 degrees, this thing is 45 degrees. So we now know the angle of incidence is also 45 degrees. Yay. Now we can use the law of reflection to figure out what this angle is. And it works out to be also 45 degrees. So we can now say what direction that light goes out of. It goes out at an angle of 45 degrees relative to the surface normal. Now, you could also ask, how much is the light bent? Like, what is this angle between the incident ray and the reflected ray? Well, that angle is just the sum of these two angles. 45 degrees plus 45 degrees turns out to be 90 degrees in this specific case. So this is just giving you a sense of how you can approach these problems. Again, you need to figure out what you want, which is often the angle of reflection, or at least the direction of reflection of the reflected beam. You know that you're going to probably use the law of reflection to figure that out, but you need to spend some time to figure out what your angle of incidence is. So this is just a fairly straightforward example. Now let's move on to a slightly more complex one. We already talked about how a single mirror doesn't work as a retroreflector. Let's take two mirrors and make a corner. So we're looking at a cross section here. Here's one mirror here, one mirror here. This one's 45 degrees tilted down. This one's 45 degrees tilted up. They form a right angle here. And we're going to shine in light straight in again. And we'll have it hit the bottom of this. After it bounces off both of these mirrors, which way does it go? Okay? So the first event is the problem we already did. It's how the light reflects off of this particular mirror. And so we already have that. It comes in, its angle of incidence is 45 degrees. The angle of reflection is also 45 degrees. This beam goes basically straight up until it hits the other mirror. Okay, that's cool. But now we have to figure out what happens here. Now the light's going to bounce off this and go in some direction. What direction is that? Well, again, we have to figure out what is the new incidence angle. And to do that, we have to do some of the same logic we had before. Again, what's relevant is where is this ray relative to the surface normal for this mirror. So we have a different ray here. We need to know this angle. This is our new angle of incidence. How do we figure that out? Well, again, it often turns out it's easier to figure out the other angle, the angle between the line of sight and the surface of the mirror. Not always, but sometimes. We can actually figure that out because we know this angle. This angle is 45 degrees. The angle between the two mirrors is 90 degrees. You can show that by geometry. And what we have here is a triangle made up of two mirrors and the ray going from one to the other. The interior angles of triangles the sum of this angle plus this angle plus this angle is always 180 degrees. So whatever this is, plus 45 plus 90 has to equal 180. Do that algebra, you'll figure out this angle is 45 degrees. Now, if this angle, now we're back to kind of where we were before. This is coming in towards the mirror at an angle of 45 degrees. That's not the angle of incidence. The angle of incidence is this. But since this angle between the blue arrow and this surface is 90 degrees, this angle is 45 degrees, this angle also has to be 45 degrees because it's 90, because 45 plus 45 makes 90. Okay. Now we can use the law of reflection. We know the incidence angle. Now we get, now we know the angle of incidence. Now we get the angle of reflection is also 45 degrees. And now we have a beam of light going back out. So now we know the direction the outgoing beam should go. And if you look at this, it looks pretty parallel to the first one. So it's coming in and going out basically horizontally. And we can actually confirm that just by looking at the numbers. So in this case, the light was originally going to the left, now it goes up. The angle between this ray and this ray is 45 plus 45 degrees. The amount by which the light was bent, because if otherwise it would go straight, is just 180 degrees minus that sum of 245 degrees, but that's 90 degrees. We've bent the light by 90 degrees. The second bounce, the direction changed by the same amount. 180 degrees would be it going straight, but then we remove 45 degrees plus 45 degrees, which is 90 degrees, which gives you 90 degrees again. So each bounce changed the direction the light went by 90 degrees. So adding those together gives a total change of 180 degrees. So the light's going back where it came from. Cool. So this thing works for light coming in horizontally. Now, a trick, this is just to show that how to think about problems where there are more than one reflections, but you can see there's some it's kind of a special case because all of these angles are 45 degrees. You might think, that's a pretty specific case. What happens if the light doesn't come in like that? What if it comes in like this? But before I get into that, I should say one other thing. There's a couple of objections to this. One is all the angles are 45 degrees, which seems like a special case. The other issue is you might have noticed the light hit this mirror first, then this one, and then this one. What if the light hit this mirror first? Turns out it doesn't matter. Here's what's fun about that. All I have to do is change the direction of all of the arrows, and then I'll get light hitting the top mirror first. If I do that, all of the geometry is the same, just the light is going in the opposite direction. Angle of incidence is still angle of reflection. So this works regardless of which of these mirrors you hit. And it works regardless of where you land on those mirrors. So this is actually fairly generic as far as position on the mirrors goes. But it won't be the same if the light comes in at an angle. So we should look at that. And that'll give us a better sense to understand what's the real angle of incidence, what's the real angle of reflection. So let's consider a slightly different case where light comes in tilted at an angle of 15 degrees. So this is a fairly steep tilt. 15 degrees is not nothing. And so it hits this surface. It's going to hit this, bounce off this, go to this, bounce off that, and come back out. What angle does the reflected signal come from? Well, we've got to treat the reflections at both surfaces. And now that's a little more complicated because we have to figure out, again, the angle of incidence. Okay, so how do we do that? Well, again, we have to define our surface normal because what we care about is this angle. Now, if you look at the way this is drawn, you can see that angle is not 45 degrees anymore, it's a little wider. Well, how much wider is it? Given that this is tilted at 15 degrees and this is tilted at 45 degrees, how do we figure that out? Well, this one makes an angle of 15 degrees from the horizontal. This makes an angle of 45 degrees to the horizontal. The angle between the surface of the mirror and this line is 30 degrees. This is where I'm going to be clear. This is not the angle of incidence. The angle of incidence is not 30 degrees. It's not this one. It is this angle. Remember, this is the angle of incidence. The angle of incidence is what we need now is to figure what that is. But we know this angle between the blue arrow and this surface is 90 degrees. This is 30 degrees, so 30 degrees plus the angle of incidence is 90. This angle has to be 60. Now, you might go, do I really need to think about that? And the answer is, for mirrors, it's useful, but it'll get really important when we start talking about lenses and refractive optics. So that's why I'm emphasizing it now. So the angle of incidence on this mirror is 60 degrees. Okay. By law of reflections, the angle of reflection is also 60 degrees, which means this angle is also 30 degrees because this is still a right angle. 60 degrees plus 30 degrees is 90 degrees. Now, you could say, why do we keep using this? Why shouldn't I just use this? This is 30 degrees, this is 30 degrees, isn't this easier? And in a lot of cases it is. The trick is we're going to have to use a similar sort of rule when light passes into materials. And in that case, this distinction matters. And that's why I'm emphasizing it now. It's good practice to know what the angle of incidence is. If you just said this is 30 degrees, so this is 30 degrees, you've got the trajectory fine. It won't screw up your math. But it will lead you to be confused when you get into situations with refraction. So we want to be explicit about this. So anyway, but now we've got the first reflection. Now we have to do the second one. This beam of light is going to reach this point. We've got a new angle of incidence we have to figure out. Okay, how do we do that? Well, again, we do have a triangle here. This angle is 30 degrees. This angle is 90 degrees still because we haven't changed the mirrors. The sum of these three angles has to be 180. So this angle is 60. Cool. So the angle between the incident ray and the surface is about 60 degrees. That means the angle of incidence is 30 degrees. So notice, the two angles of incidence are different. Whereas before everything was 45, this comes in, and the first angle of incidence is 60 degrees. The second angle of incidence is 30 degrees, so they're different. Okay, now we use the standard law of reflection. If it comes in at 30 degrees, it comes out at 30 degrees, or to the surface, it comes out at 60 degrees and comes down this way. So this is a relatively gentle bend. This is a relatively steep bend. So we've now got the trajectory of the outgoing light. And if you look at how this is sketched, those two lines look parallel. It looks like the light comes in, bounces around twice, and comes out going in the opposite direction. And in fact, that's true. Again, these numbers tell you that. in this first reflection, this angle between the incident and reflected light is 120 degrees. So the light was bent by 180 degrees minus 120 degrees by just 60 degrees. It wasn't bent very much. The next bend, this to this is 60 degrees, but that means this light went through a bigger bend, so it's 180 degrees minus 30 plus 30, that amounts to 120 degrees. So that was a bigger bend. So we go through a 60-degree change in direction, followed by a 120-degree change in direction. The total change in direction is exactly 180 degrees. The light still goes back where it came from. So you can have this light come in at fairly steep angles and still have it work. And again, it doesn't matter what order you hit the mirrors in, it'll still work. So this corner is actually pretty good at reflecting light from a range of angles, as long as the light is in this plane of the drawing. The one thing I'm not doing here is having the light come into or out of the page, just because drawing that gets really hard. Turns out if you want to do that properly, you do need a third mirror. This is what are called corner cube reflectors. They're just literally 3 mirrors put together in the shape of an inner corner. This works in all 3 dimensions. You send in any light, it bounces off all 3 surfaces and comes straight back where it came from. And again, this isn't just like this problem. When I chose 30 and 60, because I chose an initial angle of 15, I can choose pretty much any angle I want. And those of you who like algebra can do this, and it will work out. This is fairly generic. So a simple set of 3 mirrors is something that will redirect light back to where it came from pretty much any angle by which light can come in. And it does this to a high degree of accuracy, even if, you install this thing slightly tilted, it'll still work. This just shows how the law of reflection be used to develop things. The moon is very far away. And so trying to figure out things like its distance and more specifically its motion, which is related to how it raises tides on Earth and the history of the Earth-Moon system. If we want to measure the distance to the moon, we can fly spacecraft there. That's expensive. The other thing we can do is basically use this thing, which is just a whole collection of these. You shine a laser from a telescope at this thing, that laser light comes straight back to you. It isn't scattered in all directions, it comes straight back to you, so you get a really strong signal. And this allows you to measure the distance to the moon, because you now know, because you can send a pulse of light, know it'll come back to you, and just figure out how long it takes to do that. One of your problems is actually to do that sort of thing. And turns out you can get the distance to the moon to within centimeters. Given how far away the moon is, that's pretty cool. Just to say, none of the problems you're going to work on using the law of reflection are quite this complicated. They usually involve just one reflection. But I did want to go through this for the sake of showing you how you can use this to engineer particular optical elements. And it's just to get you a sense of how to approach these sorts of geometric problems as we move on to more complicated ones, which we'll deal with in the next part of the class. Thank you very much for your time and your attention.